This is part 3 of the Module 5 lecture. In this section, we're going to talk about the binomial probability distribution. And we're going to divide this topic in about 2 or 3 recordings. First, I'll introduce the binomial probability distribution. Then we work a few examples. And then we move on to the next probability distribution. All right. A binomial experiment, and a good example of a binomial experiment is flipping a coin. So think of the flipping the coin as we go through the characteristics of a binomial experiment. This is very important because this determines exactly how the probabilities are calculated. So there is a number of n identical trials. The trials here is flipping the coin or performing the experiment, and you flip the coin in exactly the same manner. So you're doing exactly the same thing. So we say that we have n identical trials. And maybe let's say that you're going to flip the coin 10 times. So n will be 10. And every trial has only 2 outcomes, either success or failure. And what is success and what is failure depends on what is your interest in the calculation of probabilities, as we will see. All right, the probability of success, we're going to use the letter pi to designate the probability of success. And so the probability of success pi is the same for each trial. And because there's only 2 possible outcomes, then the probability of failure is just 1 minus pi, the complement. And again, is the same from trial to trial. So when you flip a coin, the probability, let's say the success is tails, so the probability of getting tails is 0.5. And the probability of getting heads is obviously 1 minus 0.5. All right, now as you flip the coin, you do it in exactly the same manner, and you're using a coin that doesn't favor in either face. So the outcomes of every flip are independent of each other. So in here we say the trials are independent. And the random variable counts the number of successes in those n trials. And here, if you're flipping the coin 10 times, so we're going to do it 10 times, and we're going to count how many successes, how many tails were obtained when you flip the coin 10 times. So these are the characteristics of a binomial experiment. And before we introduce the formula of the binomial experiment, or rather the binomial probabilities, let's see how these probabilities are obtained. All right. So let's consider an example. So in this study, it considers the effectiveness of performing an anterior cruciate ligament surgery, or ACL, of the knee. So in this particular case, 3 surgeries are selected at random, and it is known from the history of these surgeries that the probability that a surgery is successful for the patient is 0.85. Now, the surgeries are performed following a very strict protocol. And so, and then the interest of the study, as we said, is on the frequency of failure of this type of surgery. So we're not interested in the success, but whether they fail. So this is the event of interest, if you will. So they're asking us 2 things. Determine if this is a binomial experiment, and they're asking us to construct the probability distribution for this experiment. So we're going to use these characteristics and see, or this description of the experiment, and see if the performance of these surgeries is a binomial experiment. All right. So the experiment is performing a surgery. These 3 surgeries follow a very strict protocol. That means that we can assume that the 3 trials, the 3 surgeries, are identical, and that we have n identical trials, or rather n equals to 3 identical trials. There are only 2 outcomes: either the surgery fails or the surgery is a success. Because the interest of the study is on the failure of the surgery, in our case, what we call success refers to a surgery that fails, and failure refers to a surgery that is successful. So again, this comes from the interest of the study. All right, so from that point of view, the probability of success is 0.15. And the probability of failure will be 1 minus pi, which is 0.15. I'm sorry, pi is 0.15. The probability of failure is 1 minus pi, which is 1 minus 0.15, which is 0.85. This is what they gave us in the problem. But because what we designated as success and what a failure, that's what we assign the probabilities. All right. The next characteristic is that 3 surgeries are randomly selected from all surgeries, so we can assume that these surgeries are independent of each other. And finally, the random variable is counting the number of successes, in this case, failed surgeries, in all n trials, 3 trials, because there are 3 surgeries. So in this case, the random variable will assign the values 0, 1, 2, or 3. 0 if all the surgeries are successful, 1 if one surgery fails, 2 if 2 surgeries fail, and 3 if the 3 surgeries fail. All right. From this we can see that this is a binomial experiment. So now with that in mind, let's use these characteristics to obtain the probability distribution for this experiment. All right, so here I'm using a tree diagram to enumerate the possible outcomes of these 3 surgeries. For example, the first surgery has a chance of 0.15 of being a success from the point of view of the experiment, and 0.85 probability that it fails, that is a failure, that is from the point of view of the experiment. So, and then in the first surgery we have success or failure with these probabilities. Then in the next surgery we have success or failure if the first one was a success, or success or failure if the first was a failure. And for the third surgery, now we have again success and failure, depending on, like on this branch, it was success, success, and success, then success, success, and failure. And the probabilities associated with each of the cases. So as you can see, I listed all the possible outcomes, and they are here. So for example, if we follow this branch, the outcome will be success, success, success. So there are 3 successes in that case. And the next branch is you have success, success, and then failure. So you have success, success, failure, and so on. So you can see that I listed the sequence of the 3 outcomes of the individual surgeries, depending on what sequence they occur. All right, so now we have the outcomes and we have the individual probabilities of each of these outcomes. All right, so the next step is use this information to calculate the probabilities associated with the values of the random variable. So the random variable, in this case, we have values of 0, 1, 2, or 3. All right. 0 will be assigned for the outcome failure and failure and failure. So all 3 surgeries fail in a sequence. A value of 1 will be assigned whether we obtain a success and a failure, or a failure and a success and a failure, or failure, failure, and success. You see in those 3 sequences there is only 1 success. A value of 2 will be assigned when you have 2 successes in the sequences. There are 3 possible sequences with 2 successes and 1 failure. And finally, we assign a value of 3 when all 3 surgeries are a success. And I notice that I use the words and or. And designates joint probabilities. The or is designating the union of these probabilities, or of these events, if you will. All right. So let's look at an example. Let's calculate the probability that the random variable will take on the value of 1. That means there are 3 possible sequences: success and failure, failure and success, and failure, failure and success. And we could have either this sequence or this sequence or this sequence. All right. So remember, one of the characteristics is that the trials are independent. So we're going to use the multiplication rule for independent trials to find the probability for each sequence. So in the first sequence, the probability that success and failure, well, is just the probability of success 0.15 times the probability of failure times the probability of failure, and I get this number. And because the sequences have one success and two failure, well, you see that is the same, the product of those probabilities is the same for all three cases. Then we want to see the probability that the random variable will be one success. So now we need to calculate the union of the probabilities of the three possible ways in which we can obtain one success. So there is a probability of this sequence or that sequence. And so now we're using the additional rule, and these are all mutually exclusive events. So all we do then is sum the probabilities. And you see it's the same probability, so it's the same as 3 times that single value, and that's 0.325. So this is for the case when the random variable is equal to one success in the sequence of 3 searches. All right, so now we can use the same idea and calculate the probabilities for all the possible values of the random variable. So when the random variable takes on the value of 0, means there are 0 successes. That means I have only one sequence of failure and failure and failure. So there are 3 failures observed. So the probability that x is equal to 0 is 0.85 to the third power, because these are independent events. And so the probability would be 0.85 to the third power. Now, we saw this case where the random variable is equal to 1, and there is only one success is observed. There are 3 sequences, and the probability that x is equal to 1 is 3 times these products of probabilities. And then when the random variable takes a value of 2, or in other words, when we observe 2 successes, well, we have 3 sequences, and so the probability that x is equal to 2 then is 3 times the sequence of 0.15 times 0.15 times 0.85, because these are independent outcomes. And here's the probability. So the random variable will take on the value of 3 when we have 3 successes. So that there is only one sequence, and that will be 0.15 times 0.15 times 0.15, or 0.15 to the third power. And that's because these events are independent. So this is then here we have the random variable and the probability that the random variable will take on each of those values. So here's a probability distribution with x equal to possible values of 0, 1, 2, or 3, and the corresponding probabilities. All of these probabilities are between 0 and 1, and they add to 1. So this is a probability distribution, and in fact this is a binomial probability distribution for 3 trials with a probability of success of 0.15. All right, so this is an interesting case of how the random variable assigns values to the number of successes, and this is it gets a little complicated to see how many successes there are. And I choose only 3 trials. Imagine this with 20 trials. Well, that'll be very difficult to calculate. And that's why then we, instead of doing what we just did, create a tree diagram, calculate every probability, we will rely on what is called the binomial probability formula. So the probability that exactly X successes are observed in n trials in a binomial experiment is given by this formula. So in this, you recall from chapter 4, this is the formula for combinations, and this calculates the number of ways in which X successes can occur in n trials. This is the probability of the joint probability of X successes, and this is the joint probability of n minus X failures. So if we have n trials and you have 3 successes, well, I mean, if you have 5 trials and 3 successes, then you must have 2 failures. So that's how this equation works. Now, I want you to know that the value uses a slightly different nomenclature. So they use probability of X instead of probability of X equal to little x. And they use P instead of pi and Q instead of 1 minus pi. And I don't use these letters because these are used for sample statistics, not for population parameters. And I wanted to emphasize that we're dealing with population parameters. Okay, I will stop.